All right, so first off, I apologize. This is shortly after school, so you may hear some noises from the halls, but they released earlier today, I believe, the free response questions for the 2026 APC Mechanics exam. And had some students ask about it, so I figured I'd try and do a video walkthrough on this. I'll try and get these posted around the same time with the AP1 that I fell behind on. I have not had a chance to actually write up what I think would be the grading rubric on this, so not only am I going to try and do a walkthrough of how you would solve this and kind of explain it, not only for students who recently took the exam who might want to see how you would approach this or what was presumably expected of you, but also, more importantly, maybe many of you watching this are for future exams or part of the class or something like that, where you're seeing this. These are great examples. In fact, we're going to take a look at question number 1, which I believe online there was a lot of pushback against, which I can understand that. I actually really like it. It's a great question. It's a drag force question, and it's also, for students who have had me before, this is a systems question. There was a lot of me going, oh, that's Cleophas. I'm going to make references to that. If you want, you can check my lessons to get more insight into that, but I'll try and explain clearly to people who are not just my students the walkthrough on that. My other videos for AP1 were a bit more delayed, but I had gone through and made what I thought would be a good representation of the scoring rubric. I've been teaching these classes for over 10 years now. I've seen quite a few of the scoring rubrics, though I'm not muckety-muck or anything at College Board, so take any of the things that I say or predict with a grain of salt. But I have seen a whole bunch of these grading rubrics over the years, and I have kind of an idea of usually where the points come in. Now, this is only the second year after the major redesign for APC Mechanics, so we are seeing some changes and trends, but I will kind of bring in the stuff that I've seen before, and I think that I'll be fairly close to being able to identify where the points are. But let's dive into question number 1. This is the math routines. If you're watching this in preparation for a future AP exam or a mock or even stuff in my class, as a reminder, the math routines question is worth 10 points, recommended time about 20 minutes on any of the physics exams after the redesign. So basically when you're watching this. The math routines is almost always going to be one of the most mathematically complex questions, no matter what exam you're taking. Now, if you're taking the algebra-based exams, that usually means it's a bit more challenging. You'll probably be challenged by it. If you're taking one of the calculus-based exams, here's where they're going to give you a really tough question. Most of the time, it's actually going to be calculus-related. Not always, but many times it's going to include at least some calculus. So if you're preparing for an upcoming exam, I'm going to give you the advice that I usually give my students. When you get to the free response, maybe skip over question 1 and go straight to question 2. Question 1 is probably going to be one that is much more challenging. And if you start with that, maybe it might put you in a bad headspace. Maybe you lose some confidence that would pay off better on some of the other questions. So just a bit of strategy. If you're watching this shortly after I've posted it, in response to taking this, hopefully you have that advice. I don't know, but think about that for the future if you have any other physics exams that you'll be jumping into. Okay, now that that's out of the way, let's take a look at the question itself. I do not have the grading rubric, or my best estimate of it, I should say, put together yet, but I will try and put that together and hopefully post it down in the comments once I have that. But let's take a look through. A box of mass capital M slides to the right on a horizontal surface. A small cube, also of mass capital M, is inside the box. The cube is against the right wall of the box and the bottom of the box, and above the bottom of the box as shown in figure 1. The coefficients of static and kinetic friction, let me zoom in just a little bit, between the cube and the wall of the box are mu sub s and mu sub k, respectively, where mu sub s is greater than mu sub k, which is kind of the regular boilerplate stuff. I'm going to pause here for just a moment and point out. Hopefully, my students, or any of the students, you're thinking through about the setup. There have been a few sample questions that we've seen before with the standard AP materials, but we're dealing with a block that is basically, box is slowing down, block is up against it, and because the box is applying a normal force onto the cube, it has a force of friction, and as long as this thing stays where it's at, that means that it has no net force in the y direction. This will be an important part of the problem, I'm willing to bet. But we could then surmise that the force of friction, static friction, points upward because the box would try and slide down, so it would oppose that, but it is not sliding, at least initially. And Before it begins sliding, the force of static friction would be equal and opposite to the force of gravity, not because of Newton's third law, but because of Newton's second law. Okay, I just wanted to point that out. We've got basically, the only reason the box doesn't slide down is because this whole thing is slowing down. What does that mean physically? Because it can be hard for people to kind of imagine that. I want you to imagine that this is a car and this is you, and someone's slamming on the brakes. Well, you would feel like you're being pitched forward. That's actually your body trying to move forward. And the seat belt, because you would definitely be wearing a seat belt, because that's the smart thing to do, would push back against you. The normal force of it pushing back against you, one, helps you slow down, which is very good. And two, would allow for a normal force that would then apply some friction as well. Greater normal force, greater friction, as we're going to see. Okay, that's what's happening with the box and the cube. The speed of the box is decreasing as a result of a resistive force. So this is basically a drag force question that is exerted on the box. But please note, on the box. This is a place where I bet a lot of students probably missed out on a few points because you really have to keep track of what objects the forces are being applied to. The resistive force is being applied to the box, not the cube. The resistive force F sub r is modeled by F sub r equals negative BV. So we have a linear relationship between our resistive force and our velocity. So it's kind of the, for want of a better term, the easier of the drag force equations that we might deal with, where B is a positive constant and V is the velocity of the box. Friction between the box and the horizontal surface is negligible, so we're just treating the resistive force as the thing that's slowing it down and ignoring the effect of regular friction, if there is any, at least between the box and the ground. Okay, at time t equals 0, the box cube system slides to the right with a speed v naught. For times greater than 0 but less than t crit, a critical time, which my mind immediately said that's probably going to be when when the cube begins to slide down. The cube remains in contact with the wall of the box at a constant height above the bottom of the box. Oh, that's exactly what I thought it was. So at the beginning, from 0 to t crit, the cube is sitting at this spot, not sitting because it's in motion, but remains at the same height above the bottom of the box. After t crit, the cube starts sliding down. That's what this thing is saying. At t equals t crit, the cube begins sliding downward along the wall of the box. Okay, great. Now that we've introduced all the information, we can jump in to the difficult parts. A few things that I'm going to point out to you if you didn't notice it. They have bolded the instruction word. The instruction words give you an idea of how difficult that part is going to be sometimes, but most importantly, give you insight into what we're expecting as an answer. If you didn't notice it, A1 says determine and A2 says derive. We're going to see how that works out in just a moment, but the magnitude of the normal force exerted on the cube by the wall of the box is Fn. Part A1, determine an expression for the magnitude of the acceleration of the cube. Express your answer in terms of m, Fn, and physical constants as appropriate. Now, one of the things that I want to emphasize on this, determine means we're looking for you to just tell us functionally what the answer is. That's more or less what it is. Determine broadly means we do not need to see your work in order for you to get full credit. It's kind of the takeaway. I'm not going to tell you that that's what it always means, but usually when you see determine, that's a clue that what you're doing probably isn't that intensive on work. I've had plenty of times where students look at these parts where it's a very intimidating question and they don't realize that some parts of this may be very easy. They're looking for determine an expression for the magnitude of the acceleration of the cube. That's the other thing to keep in mind. So I'm going to come over here. Let's go A1. If I want to find the acceleration of the cube, I need to draw a free body diagram of the cube. Well, we have a force of gravity, that's capital mg, because the mass of the cube is capital M. At least at the beginning, until it begins to slide, and I guess even when it does begin to slide, but before it begins to slide, we have a force of friction up that would be equal and opposite to the force of gravity, resulting in no acceleration in the y direction. We have, with the wall of the box here and my cube here, the box is applying a force to the left, that's Fn, onto our cube. Remember, the cube is like you in the car, and the box is the seat belt. It applies a force onto the cube, the box does, to the left, and the cube applies a force of Fn onto the box to the right. That's going to show up in our next part. but it is very important to keep track of which objects you're working with because it can slightly change how you solve this. Okay. In the y direction, I'm going to write this down real quick, but we'd have force of friction minus our force of gravity is equal to 0, at least until before we have T crit. We'll come back to that later, but the big thing that we want is this. At all points, we would have our only force in the x direction is going to be negative Fn is going to be equal to our mass times our acceleration. In this case, I'm trying to find the acceleration of the block, or sorry, not the block, the cube. I keep saying that, I apologize. Well, I just want to find this. This is the acceleration of that. Well, here's my Newton's second law. In case you weren't following along, I'm doing sum of forces in the x is equal to my mass times my acceleration in the x. I also don't necessarily need to worry about showing the equation that I'm starting with because it says determine. Determine means we're not really looking for work. You might be able to get some partial credit, but usually determine means we're just looking for the answer. In this case, I could then divide both sides by my mass, and I would get that my acceleration is equal to negative Fn divided by capital M. They haven't necessarily defined the direction, so this could still be positive. Let me double check. They don't necessarily define a direction as positive, so you could have this as positive or negative. But most importantly, determine an expression for the magnitude. So in this case, to find the magnitude, we would drop the negative. I believe that this part, A1, is worth 1 point, and it is simply for having a correct expression for the acceleration of the cube. Now, you may have started looking at the box because there's a lot going on with the box. The box has more forces being applied to it, but in this case, the instructions tell you to look specifically at the cube, and that's your clue to look at this. For students who have had me in class, the cube is Cleophas because it has the simplest free body diagram. Look back on our lessons for system and object and take a look at that for train cars. Okay, so A2. So A1, I feel very confident that it is worth 1 point for having a correct expression for the acceleration of the cube. We can also see our acceleration is equal to Fn divided by m. Those are exactly the things that we're allowed to answer in terms of. They do also allow you to answer in terms of physical constants as appropriate, but there isn't really much else that you could bring in. And I will say this, if you did want to try and make this more complicated and connect it to the friction, even though you don't need to, the frictional relationships will depend on what time you are in the motion, because the force of friction, its relationships will change over time. Okay. Let's jump forward to A2, moving forward. A2 is where it gets a little bit more complex, and your clue on that is derive. So I want to emphasize that because in my class, we always emphasize what your instruction word is to give you insights into how you would go about solving it. Part A1, I'm pretty confident is worth just 1 point. A2, I believe, I'm predicting that one to be about 3 points. It might be 4 points, but I think 3 points for A2, and I think 3 points for the graph here. It might be that the derive is 4 points and the graph is only 2. Again, they're changing things up a little bit with the redesign, but classically, I feel like this is probably 3 and this is probably 3, but give or take a little bit. Okay, so on this, derive. What are we deriving? I'm getting ahead of myself. An expression for Fn as a function of t from t equals 0 until immediately before the cube reaches the bottom of the box. Express your answer in terms of capital M, B, V naught, T, and physical constants as appropriate. Begin your derivation with a fundamental physics principle or an equation from the reference sheet. And this one's tough. Okay, I'm going to bring up something, and if there's time at the end, I will actually set up for us to do both derivations. But there's something that you need to keep track of here, and it's how you're going to go about solving this problem. You have one of two approaches. One, look at the box alone, or the box cube system. You may or may not be cognizant, know the reason that there's a difference between this, but hopefully by the time we're done, you will understand that. So if I'm looking at the box alone, here's what my free body diagram looks like for my system. Once again, to solve this, we're going to need to work with forces and accelerations and so forth. So we got mg down. I'm just going to call this F, not Fn. It is a normal force from the ground holding the box up, but that's not something that I want to deal with at this point. I also technically have a force of friction down, but I'm not interested in the y direction. I'm really interested in the x direction. For the box, it experiences Fn to the right from the cube, and it has the resistive force applied to it to the left. I also know that my resistive force is greater than the normal force because the box is going to slow down as a function of time. This is the free body diagram that we would use if we are using the box by itself. The total mass, m total, of this analysis would be capital M because I'm only looking at the box. I can also do an analysis based off of the box cube system. And that one has upsides and downsides in the logic of setting it up, but I will draw out my free body diagrams for this. I have that this has a force down of 2 mg. The total mass of this system, being box and cube, is 2m. I have a different F, I'm just going to call that F for the vertical, because again, I'm not interested in the vertical forces. Now the normal force becomes an internal force, and I don't need to actually include it for my free body diagram, because it won't change the overall. I have just the resisting force off to the left. Now, I have actually, I'll show you the notes on this, I have solved this both ways using both systems, and you will end up with the same answer both ways, but some of the steps will be slightly different. In this case, for my students and any other students, even if you don't have me specifically, if you're using this to study for the future, this is one of the reasons why I keep referencing Cleophas. It's a memorable name for a lesson that hopefully embodies a lot of this. This is the easier of the free body diagrams for us to work with. Yes, it does not have the normal force in it, but we just found, and here's the other thing, in part A1, we found that the acceleration of the cube was equal to Fn divided by m, or writing it differently, we had that our normal force was equal to our mass times our acceleration of the cube. So if I can find my acceleration, I can put it back in here and get an easy approach to my equation for the normal force. That being said, if you're just looking at regular problem solving approach, maybe you wouldn't want to use the box cube system because it does not have the normal force as part of your setup. You can do the box alone, but it does require a bit more complex analysis, partly because it has additional parts of it. I would recommend working with the box cube system, and that's what I'm going to try and walk you through here. Okay, I'm going to begin my derive. What would I write? I would write Newton's second law. My sum of forces is equal to my mass times acceleration, or as it appears on the equation sheet most recently, my acceleration of my system is equal to my sum of forces divided by my mass. Start with an equation from the equation sheet. My bet is, as long as you have a clear indication that you are starting with Newton's second law, and then taking the steps after that, you would get the first point. The first point I expect is going to be for a multi-step derivation starting with Newton's second law that is possibly even properly applying it to an appropriate system. Okay, going to my appropriate system, I have negative Fr is equal to our mass times our acceleration, and I'm going to put a negative in here because our acceleration is also going to be to the left. You can make to the left the positive direction. There's going to be some issues with directions in here as we go through. But we end up with the following, basically, that Fr, our resistive force, is going to be equal to, oh, I'm sorry. And here I am making my own mistake. This is my net force, and it needs to be equal to the mass of my system. If I'm looking at the box cube system, it is not m, it is negative 2m times a. So I would have 2ma. Here's one of the places where things change. If you're setting this up for the box alone, you would have an additional force, Fn minus Fr, and it would be equal to m times a. In this case, my analysis, I'm using a different approach, and I would use 2m instead. Okay, so with this, I might check my notes, but let's see how well I can go through on this. My resistive force would have a magnitude. I basically have the directions taken care of in this. So I'm going to have BV equals negative 2m dV dt. Okay, so I'm going to go ahead and mark this. I don't know if it's right here, but for many, many years on questions like this with drag force, correctly setting up an appropriate differential equation that could be used to find what you're looking for, usually the velocity, is usually the next point. So you would get 1 point for being able to set up Newton's second law and do a derivation on that. The second point would be for a differential equation. In other words, getting this set up properly, replacing A with dv dt, and having everything else, things that you're allowed to answer in terms of B, yes, and M. V has to be in there because we're solving for a function of time for our velocity. We actually are going to use that to find our normal force. But here's how we're going to work with this. Okay, the rules on this, how you do this. You want to try and get all of the stuff with a V on one side and all of the stuff that doesn't deal with V on the other. So I'm going to do a couple of steps mathematically. Feel free to stop and follow along, but I'm going to move everything. I'm going to move dt over here and 2m over to the left-hand side. I'm going to move v to the other side, and I get the following. b over 2m dt is going to be equal to dv over v. Okay. Now that I've got this, I have my differential equation. I am going to point something out here. I'm going to put a little asterisk. We're going to come back to this. There is a good bet that that should actually be negative dv dt, or you could claim that the negative goes in here, but I don't think that that's actually the best way of approaching it. A small side note on this. The negative would be there because dv dt is describing how your velocity is changing as a function of time. Your velocity is going to decrease as this thing slows down. So our actual dv dt would have a negative to it because that's what ends up happening. As a side note, for those of you going on to APC E and M, this is also something that shows up where there's a difference between how you do this differential equation if you are charging a capacitor or if you are discharging a capacitor. When you are discharging a capacitor, for the same reasoning, you have to include a negative. When I first solved this earlier, I overlooked the negative because this should be, I think, the appropriate approach, but I'll tell you why I tracked down this issue in just a minute. Okay, so now that we've got this, I am going to do the following. I don't want just dt and dv. I want to actually integrate this to find the actual values. So I'm going to go from 0 to t here, and I need to integrate the other side, and it's going to go from my initial value, v naught, to whatever the velocity is at a given time t. So this may also be, I don't know how they're going to treat this. Again, the old exam usually had it where you would have one for properly setting up the differential equation. The new exam looks like it's been favoring the integral form more. So having an integral form with proper limits of integration, or integrating it and keeping a constant of integration and then attempting to solve for that would be where that point would come in. But I think it's right around here that you're getting your second point. For this portion. Okay, with this, I would end up with the following. The left-hand side becomes bt over 2m, and that's going to be equal to the natural log of v evaluated from v naught to v as a function of time. In this case, this would end up being the following: natural log of vt minus the natural log of v naught. That's how I would set up and evaluate my limits of integration. And by the rules of logs and exponents, we'd end up with the following. I could rewrite this as natural log of vt over v naught. There are other ways to do this, but I cannot stress this enough, especially if you're using this to study for either the mechanics exam or the E&M exam. This is one of the most useful and simplest ways to get the answers that you're looking for with our actual derivations. So on this, make certain that you've brushed up on your rules for exponents, exponential functions, and logs, natural logs. So we end up with bt over 2m equals this. Okay, I need to get vt out of this natural log. So I undo that by raising both sides to, or taking e raised to both sides. E and natural log are going to cancel each other out, and I get my next step. E raised to the bt over 2m equals, we've got vt divided by v naught. I can multiply both sides by v naught, and I end up with almost the answer that we're looking for. This is what I did earlier today, bt over 2m. And then the moment I saw it, I knew it was actually coming because I had felt from all of my practice with it, this needs a negative. At t equals 0, this returns the correct answer, that v of t is equal to v naught. However, this equation, as t gets bigger, as time goes on, e gets raised to a bigger number, and we end up with a velocity that is greater than v naught. That's not what actually happens. I knew that I needed a negative because I need this to decrease over time. My bet is if you did all of this and you actually caught that and put the negative in, you would probably still get full credit. I don't know for certain. Back up here, I had mentioned that this, we'd come back to this. Here is where I believe the negative actually comes in, and for the reason that I mentioned. As the derivative of the velocity as a function of time, it is slowing down, it is decreasing over time, so that means that this would have a negative value, and that's where we introduce that. It might also be that when you replace FR, that you would end up with negative BV. That might be embodying the same thing, but I don't know. And that's why I'm emphasizing this, because once again, it has applications, the logic does, in a later class as well. Okay, moving forward. This sets us where we have our velocity as a function of time. This does look like what I would expect it to. And my recording's been going for a little bit, so I'm going to check my recording. We'll be back in just a minute.